Today's seminar is going to be by Anaïs Rouanet on association between sex and cognitive aging. Anaïs, the floor is yours.
Thank you. So I'm going to speak in English because maybe some collaborators, American and English collaborators, are going to join us. So to give you a bit of context, so I'm a postdoc in the Biostatistique team, for the one who don't know me. So 2 years ago, I had the chance to join the MELODEM Consortium, which gathers international biostatisticians and epidemiologists on methods for longitudinal studies in dementia. And so we had a data workshop where, along with all these people cited here, we worked on the association between sex and cognitive aging. And in particular, we compared different methods, cognitive measures, and aging cohort studies. And so this year, we decided to resume this project and to finalize it, highlighting the reasons why the estimation of the effects of sex on cognitive aging is so difficult on cognitive aging cohorts. So first, the study of sex and cognitive aging has raised great interest in the community of AD research. However, the literature has raised very heterogeneous and even inconsistent results. So, for example, some works have shown that women are better in verbal memory and episodic memory, while men are better in visuospatial tests. Hyde collaborators based their work on some meta-analysis and showed that men and women were almost similar in most of the psychological variables, but including cognitive functions, and then proposed the gender similarity hypothesis. And then other authors here, Avila and collaborators, were maybe more specific, stating that the differences in memory, language, and visual spatial tests were varying as a function of race and ethnicity. So there's no real agreement or consensus on the effect of sex on cognitive aging, and some directions of explanation are that we can have, of course, differences according to sex and cognitive functions, but even given a cognitive function, depending on the test that we use, they can have different specificities that can show different differences according to sex. For example, for verbal fluency, so in this work, I'm going to use animal naming, but you could also use the ESAC test, which is more global and which may lead to different results. Then we have to account for the selection bias from the sample selection. So the nature of the population at under study, proportion of men, women, of high and low education, or where the people lived. And this is intrinsic to the population. And then we can have a differential selection with time by selection and death. And of course, the method that we use to quantify the effect of cognition may lead to different results, and we're going to see later on the different estimates that we can target. Oops. So, as I told you, in cohorts of elderly people, the follow-up can be terminated by death and dropout. So Little and Robin have proposed a categorization of the type of missingness mechanism for missing data. They define data missing completely at random if the probability to be missing depends only on covariates. Then data are missing at random if the probability to be missing depends on covariate and observed values of the outcome. And then data are missing not at random if they depend on covariate, on observed values of Y and unobserved values of Y. For example, the current value of cognition or the current cognitive decline, which are not observed because in cohort studies, data are collected intermittently. in a paper published in 2017, we extended the same assumptions to death. So we define death completely at random if the probability depends only on covariates, death at random if the probability depends also on observed values of y, of the marker, and death not at random if it depends on not observed values. And so these different assumptions will have impacts on the performances of the longitudinal model that we use. And so for such longitudinal data with dropout and death, the state-of-the-art models are population models and subject-specific models, so two types of families. The population models target the population mean and the effect of covariates on the change of this population mean, while the subject-specific model targets the change in the individual trajectory. And so I will go into more details later, but the population models are namely marginal model estimated by generalized estimating equations or weighted generalized estimating equations. And in subject-specific models, you will find the mixed model and the joint model estimated by maximum likelihood. And so in the rest, we're going to see how all of these models perform under the different assumptions of missingness and death. So the objective is to explore the inconsistency in association between sex and cognitive aging. And we will contrast different methods, different cognitive measures, and different aging cohorts. First, I'm going to describe the dataset that we are going to study here. We have access to 3CT, Packwood, Whitehall, Active, and ATNI. And that's the one I'm going to present here. So 3CT and Packwood are French prospective cohorts of subjects randomly chosen from electoral registers. In 3CT, they come from Bordeaux, Dijon, and Montpellier, but here we consider only Bordeaux. And it was initiated in 1999, and visits were made at home or in an exam center. In Packwood, it was initiated a bit before 1988. People were aged 65 and older, living independently at home, and in Gironde and Dordogne. And the interviews were done as visits were done at home. For Whitehall, this is a British cohort based on employees from the British Civil Service. It initiated in 1985, and the collection of data was made by postal questionnaire and clinical examination. Active, it's an American controlled randomized trial of cognitive training. So people were divided into 4 groups, and 3 of them have undergone training intervention on memory, reasoning, and speed of information. But here we only focus on the control group. And so people were living in community dwelling, age 65 and older in 1996, and were living in 6 different sites across the US. And finally, ATNI is a multi-site clinical study initiated in 2004 with people aged older than 55 years and recruited at 57 sites in the US and Canada. So here you have a description of the 5 datasets in terms of baseline covariates and follow-up. We have 600 subjects in active and ATNI, and more than 1,400 in the 3 other. The age range and the mean baseline age are quite similar and comparable across the studies. We have 9 years of follow-up in Whitehall, 13 in active and ATNI, and then longer follow-ups in 3CT and Packwood. And these are the mean number of visits per subject. So here we have 2 values because we consider 2 cognitive tests for 3CT and Whitehall. And we can see here that the male proportion and proportion of higher education is quite heterogeneous across the cohorts. So we have 71% of male in Whitehall and down to 30% in active. And for higher education, we have more than 90% in 3 cities with more than the primary school diploma, and down to 25% in active. So in active, we took 14 years of education as a threshold, which is the end of middle school. We considered 2 types of cognitive tests: verbal fluency, which is animal naming for these 4 cohorts, and then episodic memory, which is the sum of the 3 recall for 3 cities. So you are given a set of a list of words, and you have to recall them orally. In Whitehall, it's the same, but you had to write them down as well. And AVLT, you also have a list of words, but you have 5 learning tracks. So the test in episodic memory may be a bit more different across cohorts than the test for verbal fluency. So now I'm going to show you and try to illustrate the estimates that we can target in such type of longitudinal cohort. So first, so this is simulated data. To start with an easy context, we'll first consider a complete case study. So if we consider 200 subjects seen until the end of the follow-up, in blue lines, you have the spaghetti plots, so the individual trajectories. And in the salmon solid line, you have the mean in the population. So actually here, this is the subject-specific trajectory, which is can be interpreted as the individual trajectory for an average individual, but as well it can be interpreted as the population trajectory, because if at each time point we compute the mean of the observed values at this time point, we can see that we will have exactly the same trajectories. So when we have complete data, subject-specific and population interpretations are the same. However, because we have to deal with dropout and death, this case would represent the immortal cohort, which is a hypothetical cohort, and which is not the estimate that we are interested in. So now let's consider the same data, but with subjects seen until the time of death. So you can see that we have, of course, fewer data. In salmon solid line, you still have a subject-specific trajectory for subject alive, and actually we have shown in a paper that the subject-specific trajectory for subject alive or the subject-specific trajectory for the same subject in the immortal cohort is the same. And actually you can see that the trend of this trajectory captures the trend of all the other individual trajectories around. However, if we compute the population mean among the population alive, so it means that at each time point we compute the mean of all the observed values of y here, so among subjects currently alive, the trajectory is deviated and overestimated at the end. And this is due to the fact that here, to make it interesting, the probability to die is higher among subjects with low cognitive outcome. And so this will be the difference, or will be due to the selection, the differential selection by death. So the population alive is the population we are interested in. We are not interested in the population immortal. But we think that, we argue that when studying the effect of sex on cognitive aging, we are more interested in the effect of sex in the change of individual change. So we are interested in the difference of individual trajectory for men and individual trajectory for women alive, and not in the change in the population mean, which here will be selected because of the different selection by death. So we can talk about that later, but this will be the argument that we will follow throughout the presentation. And now, so the difference between the two here is that here we consider only the population observed. And if we do exactly the same, so the mean population among the subject observed is as well deviated and more selected by death and by dropout. So from this, we can see two things, that the subject-specific mean and the population mean have different trends. And so the effect of sex that they will estimate is likely to be different as well. But we believe and we argue that the one, the estimate we are interested in is the effect on this subject-specific trajectory for a subject alive. So now I'm going to link the different methods and the estimate that we mentioned here. Concerning population methods, marginal models that were proposed by Leung and Zeger, using unweighted GEE, actually targets the expectation of Y, of the marker, among the subject currently observed and alive. So T1 is the time to death, T2 is the time to drop out, and T is the current time of observation. And so the population currently observed may not be the one we are interested in. However, if we provided that the estimate that we are interested in is a subject-specific estimate for a subject alive, this GEE will give unbiased estimate in the case under the assumption that the dropout is missing completely at random and death is missing completely at random. However, we're still on a population level in the population observed, but yeah, we will have an unbiased estimate if we are in a MAR, MCAR, and DCAR assumptions scenario. To make it robust in the MAR, missing at random dropout, Dufil and collaborators proposed to use a weighted GEE approach. So still a population model where all the subjects and all the observations are weighted by the inverse probability to be observed, given that the subject is alive. So 1 over the probability to be observed at the current time, given that the subject is currently alive, given his covariates and the past observed values of Y. So here we're going to overweight subject alive with a low probability to be observed, and we're going to underweight subject alive with a high probability to be observed. So we are going to correct for dropouts, but not for death, because everyone needs to be alive. And doing so, the weighted GEE is going to target the expectation of Y among the population currently alive. So we are still on a population level, but this time in the population of people alive. And provided that what we want to estimate is the subject-specific estimate for a subject alive, the weighted GEE will provide unbiased estimate in the case under the assumption that dropout is either MCAR or MAR, and death is DCAR, so completely at random. Now, if we move on to the subject-specific models, so the linear mixed model that we know in the standard form, here we consider UI the random effects. So X are the covariates, the beta the regression parameters, Z the covariates associated with random effects. And so we have, this is a subject-specific model because it's conditioned on the random effects, which can be represented, can be interpreted as the individual unmeasured covariates. And we have shown in a paper that this trajectory, individual trajectory, so in the immortal cohort, is actually the same as the trajectory for the same subject, given that he's alive. And that is going to be what we're interested in. And this is true if the measurement error is independent from the time to death. So contrary to some authors which state that subject-specific models are only interesting and interpretable in the immortal cohort, we argue that they are also interesting if we are targeting the trajectory, individual trajectory for a subject alive. And so here LMM will provide unbiased estimate under the assumption that dropouts is missing completely at random or missing at random, and death is missing death completely at random or at random. If we want to account for possibly not at random dropout and death, we need to use joint models estimated by maximum likelihood as well, where we jointly model the longitudinal outcome and a time to event given the Raman effects. And the joint modeling, the explicit modeling of this time to event will allow us to account for, accommodate for missing not at random or death not at random. So I didn't put TI1 or TI2 because if we want to account for dropout MNR, TI needs to be time to dropout. If we want to account for death not at random, TI needs to be time to death. And if you want to account for both, we can either take a composite outcome, composite time points, as we're going to do in the rest of the analysis, or we can use a competing risk model. And so here the beta estimated by joint model is can be interpreted as the effect on the individual change for subject to life, and can accommodate any type of missingness or death mechanism, provided that the joint model is well specified. Now I'm going to move on to the analysis. So for the analysis, we included only subjects older than 55 years with no dementia at baseline. They had to be observed with the cognitive measures collected at baseline and no missing data for sex, education, and age at entry. So for the longitudinal model, we specify it with time being the delay since entry in the case, so here TIJ. We specify a quadratic trend with random effects of time for subject-specific models. PE is the practice effect, in order to take into account the fact that it might be more stressful the first time to take the test, and so we can observe a jump between the first and the second visit. Age at 0, it's the birth cohort effect. It's the age at baseline to take into account the birth cohort effect. And EL is education, so high education versus low education, except for active, where Alden preferred to take it as a continuous variable, and sex with 1 for male and 0 for female. So we use the same specification for LMM, GM, GE, and weighted GE. And then for GM, we define a composite endpoint, which is the minimum between dropout, dementia, and death. And if death occurs more than 3 years later after the last visit, we consider that it was dropout just after the last visit because of interval censoring of dementia. We model this composite endpoint with a proportional hazard model with splines on the baseline hazard, adjusted on education, sex, and age at 0. And then we consider 2 types of association between the composite outcome and the composite endpoint and the outcome. So either through the current level or the current level and the current slope. And then we chose the best one according to likelihood ratio test. Now I'm going to illustrate all these methods on the 5 cohorts that we have and try to understand the differences in the estimate of sex on each of them, each of the cohorts. So here you have the result on active, on memory inactive. Here, memory is, the trajectories are plotted as a function of time. I will go back to that later. Here you have the estimate of sex as a function of time. So time goes 0, 5 years, and 9 years. The difference being male versus female. So on the left of 0 is in favor of female, and right is in favor of male for the 4 models. And then you have the dropout probability and death probability according to sex. So here, let's focus first on the GEE estimation in dotted and dashed line. So in purple, you have the result for women, and in green for men. For both of them, you can see that the GEE is higher and actually represent the population mean in the population currently observed, and so selected by death and dropout, and that's why it's higher. People who stay in the cohorts are healthier or have a higher memory scores. Then in dotted line here, you have the weighted GEE, which corrects for dropout. So the difference here is due to the difference to the selection by dropout. But still, this is the population mean in the population currently alive. And then in solid line, you have the linear mixed model trajectory estimation. And in dashed line, you have the GM estimation here, which are very close. So this may make us think that the composite outcome, endpoint, is missing at random. So if we look at the estimate, we can see of sex, we can see that at baseline, the 4 methods are similar and estimate the same value in favor of female. Then we can see that for all of them, we have a decrease in the intensity. However, the decrease is higher for population models, so GE and weighted GE. And why is that? Because men are at higher risk to die, and people with low level of cognition are at higher risk to die as well. And so men who stay in the cohorts are likely to be healthier. So at the end, we're going to compare healthier men to healthy and less healthy women. So that's why the population estimate here are drifted towards the 0 in favor of men. However, for the individual, for the subject-specific estimate, we can see that yes, there is a decrease, but which is less pronounced. Now I present you the result in verbal fluency in 3C, because we have kind of the same pattern for dropout, no difference between male and female, and men die more. So if we look at the verbal fluency, this time males are at have higher scores at baseline, but we can see that the differences between the 4 trajectories, the 4 methods, are less pronounced. In terms of estimates at baseline, so you have a significant difference in favor of male. That fades away with time as well to end up not significant at 15 years. And at 15 years, you can see as well that the population estimates are as well drifted toward the right, and possibly with the same interpretation, as men are at higher risk to die, and people with low cognitive level are at higher risk to die. So we compare healthier men who stay in the cohort to healthy and less healthy women. Now we have the result on PACWID on verbal fluency. In PACWID, so this time you have a difference in dropout according to sex in favor of men. So men drop out less and die more. At baseline, male have higher scores, but then everything in the middle, we can see that everything overlap. And we have a longer follow-up, so this may explain a bit more the differences at the end. At time 0, all the methods estimate the same effect, but you have a decrease up to 15 years. And at time 20 years, then it starts to be significant again, but you can see that the amplitude is quite small. Here again, you have the population models, which are the population estimates, which are a bit higher. And the fact here may be that the weighted GEE is even higher than the GEE itself. So here we're going to overweight people with a low probability to be observed among subjects alive. And so actually we're going to overweight women because they have a higher risk to drop out. However, women are as well at a higher risk to get dementia. So this might explain why for the weight GE, if we overweight female with a lower cognitive level, we would have an estimate more in favor of men. For Whitehall, here we have no difference in death probability, and we have a very few deaths. For the dropout probability, female drop out more, and drop out slash get dementia more. We can see that the female have a lower risk at baseline, but then so the ribbon here is the confidence interval for a linear mixed model. And so we can see that all of the other trajectories are included within this confidence band. However, the GE is still higher, so the population mean among subjects currently observed. We can see that the difference between GE and weighted GE, so due to dropout, is quite high, so probably because of dropout here, which is bigger, and nearly as important as the difference between LME and GM, meaning that the composite endpoint is missing at random. Missing not at random. In terms of estimates at baseline, we have a significant estimate in favor of male. That decreases with time, and here in time equal 9 years, we have a very, very big confidence intervals. So we may consider that all of them are quite similar. In the same cohort, so still Whitehall with the same dropout and death probability, we have this time the result on memory, where female perform better at baseline, and we can still see that the difference between GEE and weighted GEE is as big as LME and GM. At baseline, the estimates have the same trend, but in the opposite direction. So at baseline, female are better, but this difference decays with time. And at 9 years, everything is not significant anymore. So now I'm going to show you two other results, which are maybe a bit more complicated to interpret. So memory in 3C, which is the sum of the three recall. So in 3C, we have here no difference in male and female, and male die more. Here, what is a bit surprising is the fact that GE and weighted GE at baseline don't start at the same point as the subject-specific models, even if they're still in the confidence band. And then, so you can still see that the GE is much more selected than the weighted GE, but yeah, these two trends are a bit more complicated to understand. However, GM and LME here are still very close. In terms of estimate, you have still the same estimate between of sex between the 4 cohorts. It decreases a bit with time, but stays still significant at 13 years. And the last, but not the best, the result in verbal fluency in ADNI. So here in ADNI, we have no difference between dropout, according to sex in dropout probability and death probability. And even if all the methods start at the same point at baseline, you have really different estimations for the 2 population models and the 2 subject-specific models. And I don't really know how to interpret that. So even if the confidence band as well is very large, because we have fewer people at the end, I don't know if any of you have worked on ADNI and may have some insight on that. So provided that this is relevant, the effect here at baseline is nearly significant, is not significant, but gets significant with time. And that's as well the only cohort where we have this kind of inverse pattern. So if we try to resume all these results and to compare the sex effect across cohorts and cognitive measures, these are the results. So first, for verbal fluency, one good thing is that the LME and the GM yields very similar estimates. So for time at 0 and time at 9 years, for 3CT, Packwood, Whitehall, and ADNI. So the differences are not in ADNI, but the differences are very small. In green, you have the significant effect in favor of men, and in purple, we'll see later, we'll have the significant effect in favor of women. So here we see we have the same pattern for 3CT, Packwood, and Whitehall, where we have a stronger effect at 0 and then a lighter effect at 9 years. It's significant here for 3CT and Packwood. It's not for Whitehall, but here again, it's not exactly the same test. I mean, the same test, but not the same period of time to give the answers. So that's why it's complicated to compare in a quantitative way. We can only compare in a qualitative way. Then for memory, the same, the LMM and GM give some very similar results. For 3T active and Whitehall, we have a stronger impact of sex on cognitive, stronger difference at time 0 compared to time 9 years. And here again, because the tests used are very different, especially for active, we can't compare directly the values quantitatively, but we see a decrease with time. So based on this result, what we can see is that even if we use the same model, the same methodology, we still have a quite heterogeneity in the results. And this may due to the fact that we have different sample selection at baseline, different selection by death and dropout with time, and the specificity of the tests are a bit different across the cohorts. However, we can see on almost all of the cohorts that the men have a better result at verbal fluency at baseline, and women have better result at memory at baseline, but both effects fades away with time. So then we want to incorporate more results because we also have access to memento, regards, YCAP. All of this may be maybe too many results, so we may not take into account the executive functioning at the end, but at least verbal fluency and episodic memory. And all these results are currently in progress. So now the key messages of this presentation is that the mixed model and joint model estimate the individual trajectory for individuals alive. while the GE and weighted GE, so GE estimate the population-based trajectory among subjects alive and observed, but which may not be the targets of interest. And weighted GE estimate the population-based trajectory among subjects alive. So it corrects for dropout, but not for death. And so we argue that the subject-specific models are more useful here for the study of sex on cognitive decline, because on the effect on the individual change for subject alive, whereas population models are more useful to define norms in the cognitive scores in the population alive. And as such, Hélène, Jacques Magada, and co-authors have proposed a weighted GE method for quantile regression. So based on this, we can see that the results are the heterogeneity can be explained by the sample selection at baseline and the differential selection by death and dropout according to death, and as well by the specificity of the test considered. So even if for a given cognitive function, the different tests may yield different results. On this work, men are better at animal naming and women better at memory at baseline. However, this difference fades away with time. And of course, all of this comparison is subject to the selection difference across cohorts at baseline and with time. So I want to acknowledge all the international people that work with us here. We also have Hélène, Jacques Magada, Jérémy Estimands, and of course Cécile in the BPH. And here are the results, the references, sorry, if you want to look at them more carefully. And I had a picture at the end to say any question, but I don't know why it doesn't show. So if you have any question, I'd be happy to answer.